So we go now to the first lecture today by Wendelin Werner. He's a mathematician known for work on random processes such as self-avoiding random walks, Brownian motion, Schramm-Lohner evolutions and related theories in probability theory and mathematical physics. Currently, is the Rose Bowl Professor of Mathematics at the University of Cambridge. He has received multiple awards, and I would highlight, of course, the Fields Medal in 2006 for his contributions to the development of stochastic Loeffler evolution, the geometry of two-dimensional Brownian motion, and conformal field theory. So I'm glad to welcome Wendelin.
Thank you very much. While I try to find the connector, I want to say a few words before I start. Of course, being one of the people who will give a longer lecture after having these very inspiring short lectures, but daunting because you feel that why would you have to be given more time at all when it works well in shorter time. But nevertheless, I will try to use this opportunity to be, of a slightly different pace and different type of, maybe talk as well. I mean, each time it's the third time I come here. The last time was like some years back. And each time I have a little anecdote to say about my connection to this place. And maybe I just want to mention that one of my grandmothers spent a couple of years here in Heidelberg, finishing high school and starting studies. But the little anecdote I want to say that in those days, which was about 100 years ago, a bit more, her father, who was a doctor, would allow her to study medicine only after she has proved to be a perfect housewife by following a class of 2 years intensive course of cooking and sewing and all sorts of things. And the key to be able to study medicine and later become a doctor was to pass the end exam, which involved knowing everything about the local Badische Küche cuisine, which is, of course, great, especially if you are a grandchild later on, then you can have very tasty meals at home. But also the end, the prize, the key to studying was being able to sew, by yourself, a very wonderful coat for men, so that she could become a perfect wife before. Anyway, so that was the little anecdote I want to share about Heidelberg. Anyway, so and so that happened around here, right? So this Haushalts schools. So the other thing I want to say is, starting with two little anecdotes. Two little stories. It's always extremely puzzling for us, when we are in front of 200 brilliant young minds, and what is sort of the general message that we can convey beyond the actual scientific content. And I guess this year even more so than last time I came, which was 2018, because the world being what it is, the world changing fast, and our experience being rooted in sometimes somehow a different world than what we're heading to now, makes maybe some of what we might convey, outdated. And also, there's this little, the little story I can say as well about that I usually say in such occasions is that little story. Once upon a time, you had 4,000 explorers who went out into the jungle to explore, how, the jungle, how is it? out of the 4,000, 50 came back. And you ask all these 50 who came back, how was it? Was it dangerous? And they all say, no, it's perfectly safe, nothing happened to me. Right? And I can't help thinking a little bit like, we are slightly put in the position of telling you, everything's wonderful, we tried random things and it actually works out, Okay. All right. So maybe one thing I want to, an additional thing I want to emphasize, and that's sort of some of the spirit of this lecture, of course. The whole concept of the Heidelberg Laureate Forum is about interaction and putting next to each other the math and computer science communities. And you hear, of course, a lot about these great and particularly important these days development sort of on the theoretical computer science and interface with mathematics. I grew up, I was born at a time where somehow, computer science didn't exist as such, and where we were told at school that, mathematics was actually fed by questions mostly from physics. That was sort of the... And I just want to make the point that, it's still the case that a lot of us, look at math questions that come from physics or are inspired in some very vague way by physics. So what I'm going to tell you about today is a bit like a story of some, playing around with some things that might be inspired by physics, but in a way that physicists would not recognize, in some way that, it's sort of more digested and, what stimulated by physics things. Of course, in many cases, these questions go back to our own experience as babies, as children, how we learn about space, how we grasp things, how things fall down, and things like that. And I can't, some 10 years ago, I remember seeing a child, looking at the window of a train and doing this on the window, trying to zoom on the, what it was watching outside. So obviously that child's experience of what reality and thing is very different from mine, and therefore that child will be able to be interested in different type of problems probably than the one I was. Right. The other thing is I'm going to use a very low-tech apparatus, which is just an iPad on which there is nothing pre-written, but I will just scribble a few things on it, as I usually do anyway. I'll tell you, few items that are not necessarily directly connected to each other. I let it to you. It's a bit like little chapters of little books. Of course, they are connected in some way, but I let it to you to decide, how to connect them. And in particular, I'm not going to claim here to do any, real physics, but I want to explain you, the way one got to these questions and sort of my own journey towards the type of questions I was looking at. And maybe one of the surprises for me when I started doing the type of mathematics I was doing is that you have these amazing theories in physics, crowning achievements of some of what the human brain can produce, the standard model and all these very, very wonderful things. On the other hand, if you ask the most basic questions about how things actually work, then usually this is not a question of interest somehow, because in some sense the rule in physics is to find some formalism that produces equations or numbers that you can then confront to experimental data. You can measure something and you see that that this formalism fits with the real world data or experimental things, but it will never tell you exactly, how does it actually work. And I was at high school. I had these most wonderful physics teachers. And I remember when we were introduced to Newton's law, I raised my hand and said, thank you very much, but who's measuring the distance, between the Earth and the Sun in order to decide what the force is going to be? Surely something has to travel back and forth. How does the Earth, what's the effect that makes that it will actually turn? And then, there was lengthy discussions, and then at some point she said, well, if you continue always asking why and how, you should rather be a mathematician than a physicist, because, this reminds me of these, people who, you observe something, and then you're asked, that's the explanation, and then you have these, stubborn, unbearable, kids who always say, why, why? And then you give an answer, say, yeah, okay, but why? And she, in some sense, to a large extent, that's correct in the sense that that's not really the type of answers that physics would provide in terms of, how does it work? So if you go on Wikipedia and something, you see something with gravitons, but we don't really know what, there's maybe, well, not clear, does it have a mass, no mass? There are fundamental questions there, which, and then the next question was, yeah, okay, the potential, Newton potential is 1 over r, 1 over the distance between points. And then you say, yeah, what's special about this function? And at that time, we were not told. And then there was this weird thing about you can always replace, make as if replace your planet by the center of mass, by a point located at the center of mass. And you said, why is that? And then the answer was like, well, that's just the way it is, it works. And then a bit later, when you study mathematics, you learn about this thing called harmonic functions. And a harmonic function is basically nothing else than a function that has the property that you take its value at a point, and you take its average value on any sphere around this point, that these two are the same. So it's a function that has an average value property, that the value at the center of every ball is the mean value in the ball or the mean value on the sphere around it. Okay, and then you learn that, what is the harmonic function? Non-negative harmonic function, you want to define, well, 1 over the distance to a point, right, is the harmonic function away from that point. So it's indeed the case that, if you take 1 over the distance to a point, it's equal to the mean value of 1 over the distance to the point on the shell. And by the way, that when you do that in calculus type things, it's not a completely trivial thing to prove, and so on. But then you realize, okay, now I got it. This has something to do with this mean value property is exactly what, tells you there's something about harmonic functions that goes on there. That's why Newton potential has to be 1 over r. That's just the only one that makes good sense. Is harmonic. And so a bit later, you study various things. And in my studies, I encountered this object called Brownian motion. And Brownian motion is just this random trajectory that starts from a point, and roughly speaking, at every infinitesimal moment in time, it sort of chooses at random one direction in which to go. So, of course, you have to make this precise, but it's this random trajectory, very wild, and by definition, somehow, almost by definition, it has sort of an isotropy property that if you start in the middle, the place at which you go out of this ball will be uniformly distributed over the shell because it doesn't have any favorite direction in which it wants to go. And therefore, the Brownian motion is very directly related to harmonic functions, and it's a very, beautiful, and the heat equations and these sort of things. And you get to see that there is this random, process around that has to do with harmonic functions, which is this Brownian motion. And that's why I said, oh, that I like. I have this old question in mind that was unanswered, and maybe I can get a better play around with these, how does gravity type things work. I want to make one important remark here, which is that in order to define the Brownian motion trajectory in some way, you could say, in some sense, the only thing you need is isotropy. Is sort of how do you choose a direction at random uniformly around you. You don't need really to be able to measure distances and how space is. So for those of you who know, will come from complex manifolds or things like that, they will immediately, they would recognize this, that somehow the only information about the geometry of the space in which the Brownian motion lives has to do with at every point you have some notion of isotropy and choosing a direction uniformly at random. So in particular, if you compress space or distort space in an angle-preserving way, which like conformal maps in 2 dimensions do, you preserve these isotropy thing. You sort of compress parts of space and dilate some others, but the Brownian motion will still be the same in both after or before compression. And so, yeah, that's one point. Okay, and now you imagine that you're stuck somewhere, as you're a probabilist, and you're stuck somewhere for a couple of months. It could be a hospital bed or stuck on a desert island or something. You don't have any pen or anything. You can't do any elaborate computations. But one thing you can try to think is, what are the simplest possible, most natural random structures that you could try to define around you without making any arbitrary choices? And of course, you can say, well, Brownian motion is one. But one problem with Brownian motion is that you need to choose a starting point. And choosing a starting point in some things requires knowing some information, like the measure on the space, or we like to say the uniform measure on space if you choose a uniform starting point somewhere. And so maybe you want to use, that's maybe too much information. But there is a variant of Brownian motion that you could try to define, and that's just nothing else than saying what you're looking for is a random loop. Whoops. Okay. I updated to iOS 26, and something bad happens here. Yeah. So I'm sure you know where to. Maybe it's just doing some. Okay, I'll try to make it. So that's a loop. And an important thing about loops is that you don't need to specify a starting point in the loop. It's just a, defined modulo, rotations of the starting point. And it so turns out that there's a very natural measure in any space on Brownian loops that you can define directly, and whose definition does not involve anything else than knowing about isotropy. So it's a way in order to say, how likely is it that a certain loop, shows up. The problem, this measure is very nice, and in particular, it's scale invariant. So it's a little bit like when you look at, the uniform measure on the infinite line. It's not scale invariant, but it has this sort of feature that some feature of that type. So when you have a measure which is not a finite measure, so it's an infinite measure, it has the total mass is infinite, like the total length of the line is infinite, and you're a probabilist, you have a very simple way to construct something random out of it. And this is what we like to call a Poisson point process, which in essence says that every object will, independently of the others, appear with a probability which is sort of proportional to this measure. So in other words, if you're on the real line, on every small interval dx, the probability that a dot will fall in dx will be just dx. So in other words, you have like some dots appear at random independently from each other on this line. And you could do the same for these Brownian loops. So you have this measure on Brownian loops. And again, I told you in order to define that, you just need to know the notion of isotropy in your space. It gives you that measure. And then I have one Brownian loop here that appeared. Another one appeared there. I have to be really careful not to... By the way, in the old days, we had this one, and that had to do with Heidelberg because what happened here, Springer had his base around here. In one of the early lecture notes on percolation theory, we had this picture, which was done, written in PostScript code, and that PDF would produce a random, something with random coin tosses, and it was like supposed to be a random structure. And I think the Springer people were still totally puzzled because in those days they didn't know how to handle these type of files. So everything was fine until the final print of the book, where this random fractal curve in the book basically ended up being a perfectly similar curve because something went wrong with a random number generator. And anyway, so here I have to be very careful with my random loops. Okay. So you have this picture of these random loops. So the way I want you to think about it is that you have space. These loops are a little bit like cracks in space that could appear with time. And they appear independently from each other. The fact that this measure is sort of scale invariant means that the picture that you're going to see, this collection of loops, is going to be self-similar in distribution. So if you zoom in everything, the picture you see has exactly the same distribution as the one you started with. There's no scale. And so in particular, you have infinitely many small loops everywhere, right? Because you zoom in more and you have small Brownian loops all over the place. So this sort of picture is fractal in many ways because the Brownian motion itself is a fractal object, but then you have this multi-scale cloud of all these Brownian loops. Right, so I didn't do any arbitrary choice here yet. But then what happens is that these cracks appear, and there's one parameter that you can play with is the time you let it evolve. So the more time you have, the more cracks appear. And there's a time where you say, okay, I take the picture of the collection of cracks at a given time. And there's one special time that has the following feature that I'm just going to illustrate in a very loose way, but that can be made very precise. So imagine, whoops. Okay. Imagine I have two loops that overlap. And you are actually colorblind. So you see the union of these two loops. And then the question is, for each of these points where these two loops overlap, do they form two loops or do they form one loop? So it's basically, the discrete level, you have two things that interact, so, intersect, so you can have a picture like that, a picture like that, or a picture like that. So you have three options. And depending on your choice, 2 out of the 3 will create one loop, and 1 out of the 3 will split this into 2 loops. And for this particular intensity of this what we like to call loop soup, collection of all these loops, it so happens that for every double point, so double point I mean either intersection between 2 different loops or a double point of one single loop, you can actually retoss a coin, probability 1/3 to be, to reassign each of the 3 possible connections, and you don't change the law of the collection of loops. right? So this loop has this sort of rewiring property that, you can have demons that walk around and, a plumber that at every double point does, this little rearrangement. And you still have this object. Another remark that you can make is that in physics, you can relate this of this particular intensity, turns out, and all this is not very old stuff that I'm going to say, it's pretty recent. You can relate directly this collection of loops, and in particular with, for each, so what is it that you can measure? Imagine you're a physicist, you see this collection of loops, what are you measuring? Well, you can measure something which is like, I take a domain, here. Oh dear. Okay, I take a domain, and you say, what's the total time spent by all these loops in that domain? What's the mass of this collection of loops that sits in this domain? And this thing is intrinsically directly related to something that in physics is called the massless free field, which is sort of, in the statistical physics expression, the free bosonic field. Particles that don't interact give rise to this type of Gaussian field. Okay, good. Resurrected, my pen resurrected. And then you remember that there is this story in physics that you were told, and again, never explained, that you have particles. And so again, I'm not criticizing physics, it's just my, the way I, talking about myself rather than physics, my perception was, you have this thing, bosons are particles that have this property that they're indistinguishable. So, they don't have a particular identity, you could swap their hats and you don't know which one is which. What you can see is, the collection of all these particles, but you don't know, when they move from one place to another, you don't know which one, went which way. They could have changed their hats and exchanged things. And this is a bit reminiscent to that, right? That means if you see the union of all these things, as soon as they overlap, then somehow each loop lost its own identity. They are part of this cloud of overlapping loops. So what I'm saying here is that you can look at the union of all these loops. You're colorblind. So first you see that. And that's the type of thing you can observe, physically in something by measuring, how heavy is the loop soup in that area of space compared to that other. And then somehow to recover the individual loops, or find the individual particles, if you say that each loop is an individual particle, you have to choose uniformly at random a way to split it into individual loops. Right, so this says, maybe there is something here, this exchangeability property, which is very elementary, might be related to something that has to do with physics. Now, what is the probability if I take a three-dimensional loop soup in 3 dimensions, like that, for that particular intensity where things change like that? I give yourself 2 points, x and y. What is the probability that x and y are part of the same cluster? Right, that they are connected by a chain of loops. Well, the first answer I say, well, is 0 because first you have to sit exactly on a cluster, and that will happen with a very, very small probability. You have to be very lucky to actually be on one of these clusters. On the other hand, you can say, what's the probability that x is some very small neighborhood, that there's a cluster that goes very, very close to x and very, very close to y, and that if this very, very close is what we like to call epsilon, then this will be proportional to some power go to 0, like with some power of epsilon, and there will be a constant in front, and that tells you, how more likely is it that these 2 points are connected, that are in the same cluster of loops, compared to the probability that these 2 points are, further apart are in the same cluster of loops. And then you find out that this this constant, this probability, is 1 over the distance. It's our friend the Newton potential, and in any domain, you will have this thing that, 2 points far, it's sort of this green function, it's sort of basically the Newton potential in any space, would be exactly the thing that is measuring, the likelihood of 2 points being able to communicate by this chain of loops. And again, in that discussion with this high school teacher, I remember, I said, surely, the sun has to send out some messages out, right, in order to reach out. But, okay, I didn't know about transients of Brownian motion or anything, but I said, how, if you keep sending stuff out, then, it has to come back, otherwise you lose something. And that didn't quite work. And so here you have something where you feel a bit more cozy because you have these loops. They don't go away. They are just loops. And now you have this thing that X connects to Y if and only if they are connected by this chain of loops, and then they maybe can swap their hats and have some information flowing back and forth. So now I want to give you a simple result, which is simple to state, and I'll slightly cheat when I state it. But it's a 2025 result, so it's a recent stuff. So now imagine, so again, warning, I'm slightly cheating. Imagine that I have these 2 points, X and Y, and you look at the picture that you obtain when you condition your system on X being connected to Y via this infinite chain of loops. So the way it goes is that this infinite chain of loops is really like you have one loop here, another loop here, another loop that goes all the way here. Whoops. Right? And then the loops become smaller and smaller, so you have infinitely many loops at the end in order to reach X and in order to take off from Y. And then you have all the other loops everywhere else. Now, this is one thing. So this is the initial model where I condition on X being, talking to Y by this, random network of loops. Now, I take something else, and this something else is I take X, takes the same Y. And now what I'm going to do is I'm going to say, well, to lay down one single telephone line from X to Y. So this is what we like to call a Brownian excursion. So it's this one trajectory, open-ended, it's not a loop, that goes from X to Y. You lay down this wire. And then on top of it, you put some unconditioned collection of loops. Exactly the same picture, but unconditioned, right? The blue is just this normal picture where X typically does not talk to Y, and then you add this one line. So now the result is that these two pictures are the same. So that this has the same law. So of course, now there's a caveat, because normally you would immediately say, wait a minute, something is not right if you say this has the same law. But before I come back to that, that means sort of saying that X and Y are connected via this chain collection of loops. In terms of, this occupation field type thing, has exactly the same effect of X and Y talking to each other via some direct line. And the rest of the world doesn't know about it. All the other loops are, apart from this line, they're just, independent. So now it's a bit like, X connects to Y, has the effect of actually, they exchange the information, but nobody else knows about it. So I remember when I first stumbled into that, I said, no, that's, that cannot be true. Something is wrong in that statement. So, you look for the mistake. And why do you believe it's wrong? Well, there's a parity thing here. Here in that picture, right? because it's a chain of loops that connects X to Y, then in some sense you have two paths, right? That, in this chain of loops, you have two paths that go from X to Y. Whereas here, it's one. Right? So, if you try to do any sort of discretization, then there's a parity problem. The number, the number of paths, you draw a ball around X, and the number of paths that traverse the boundary of the ball will have to be odd on one side and even on the other side. Something doesn't work. But in some sense, it's very important that when you do the same, that it has the same law, you have to allow two things. The first one, of course, you are colorblind, so you don't see the blue. The red and the blue at the bottom have the same color. And the other thing is that you are doing, instead of looking at the union of these loops and their clusters, you are allowed to take the closure of the clusters. So in particular, what happens is in the first picture and the second pictures, there will be points in these clusters that will not be on any loop. There will be points here on this red simple path here, or points on these double paths there, that are actually, not, they are very exceptional points, but they will be not, on any single, this point here, for instance, will not be part of any loop here. It will only, in the other picture, will be only reached by an infinite chain of loops on both sides. So this is a bit reminiscent of things, again, from quantum type world, where we say, did a particle go through here? We know there's a connection. Did the particle go through here, or did it go through there when it went? And then you say, well, if we're on that picture, basically at the end of the day, you will have something. Well, so if you only see the picture, the probability that the path went here and there or there is actually a half. You don't know. If you just observe this field, the thing you can measure, to see if actually a loop went exactly there, or whether this is just a chain of loops, is different. So in some sense, the way you want to go from this picture to that, and this is sort of explaining the parity thing, is that you have some plumbers that have to rewire everything. But because of here you're going to decide that this is connected to that you're going to split this in two, but then this plumber will, have a cascade of, other, each time you do something, then you have to correct it at lower scale, and you have to correct it at lower scale. And so you do this rewiring down all the way to scales going down to, infinitesimal, that preserves the law, but that is still, that explains sort of this parity issue here. Right. So there are a number of variants of this little game you can play. That I'm not going to illustrate, but it's just to explain that sometimes still, some basic, questions that, so it happened to be related to physics and some, but it's sort of empirical, questions we never got the answer to. And sometimes when you see some math structures that, might be a tool to, play around with that direction, is still a source of inspiration for mathematicians this day. And of course, you could say, why am I more satisfied with that formalism, that type of idea, the idea that you have loops around us, and that's how we, this pen will fall down because there are some chain of loops going on. It does make more sense than saying Newton potential is 1/r. Is it more real or not? Well, it's just I'm a probabilist, so I like these, I like Brownian motion and I like the structure. I'm not saying there's more into it, and I just like to think about them, and that's sort of the reason why we are going to that. On the other hand, if you Google, then you see there are keywords, loop gravity, and all sorts of things. So it's not completely unrelated to some direction that physicists had been thinking about. But there's one really important message here that is very apparent in the way, in the problem and in its solution, which is that if you are, if you're looking at the interface between theoretical computer science and math and probability, the type of randomness and the type of random structures you are usually looking at are intrinsically discrete. You choose something in a countable set of, it's a bit like more combinatorial feature. And here, what happens here is that when you mix randomness with continuum structures, so with a continuum, when what you're choosing is sort of course, choosing anything at random boils down to doing something, countably many coin tosses in some sense, but still, these structures have these continuum features, and that sometimes when you mix these two things, some very subtle things can appear that might actually, have escaped, from our radar, and in particular might have escaped from the radar of the other, type of approaches to this problem that don't involve these random continuum structures. And so, if you talk to a theoretical physicist today and you ask him, what's the, where did you learn about Brownian motion? And they say, well, that's Einstein's paper where he produced, the Avogadro number. And you look at Einstein's paper, and basically this says, Brownian motion is just random walk with infinitesimal steps. So, you transfer the continuum problem into a discrete thing in your mind. And the whole story with Feynman diagrams and summing, over infinitely many things, is exactly doing the same. That in the head, you just say you treat these continuum structures as if they were discrete objects. But here, these type of questions, these type of phenomena that I just described, this only appears when you are looking at the continuum object, continuum space story. Okay, so I think I should stop now, and thank you for your attention. And I think the arrangement was I try to take questions myself, if there are any.
So many years ago, I was working at Bell Labs, and we observed these empirical properties we called gravitational laws. That is, like people say there's no there on the web, but we were seeing that the demand for telephone traffic seemed to have a gravitational property where the probability that A would call B depended inversely on the distance. And I think this is true on the web as well. But we weren't quite able to get exactly the right exponents that you get with gravity. And I wonder if there's a generalization to where you're going that would allow to match the empirical data.
Okay, I mean, one has to be very, very careful, of course. It's always very tempting when you discover one little thing to try to apply it out of context somewhere else. But the main message is what I said. It was, I gave the image in R3, but in something, as soon as you have any, graph or anything which, has this isotropy notion embedded in, then, this type of thing will work. But in some sense, in that case, one of the tricks has to do with the fact that, your discrete channels between, we like to think of graphs with, points and edges, and you jump, from one edge to the other. One of the tricks behind the scene is to view these edges as actual physical edges, where, the particles move around like Brownian motion on these. So, of course, if you look at the trace of when you appear at the sides of your graph, it looks like a random walk. It looks like a discrete. But for this type of collection of loops, in the middle of an edge, you might have a loop that just sits in the middle of the edge and enables you to connect, these 2 points to each other. So you have to play with these type of things to use this type of formalism I used here. And of course, that's maybe not, intrinsically discrete. Jumping from one node to the other is a click. It's not like doing a Brownian motion, hesitating, and there's nobody, in the middle of the edge waiting to, help you over to the other side. So.
Thanks. Super interesting talk. I just wanted to ask about, is there a distinction between directed loops and undirected? Because particularly when it comes to this, you were saying this super surprising fact about this kind of like law between...
So
Sorry, go on.
the answer is yes, it's an important feature. So what I haven't said, maybe, or haven't said enough, is that this collection of loops I was looking at are not directed. So in particular, when you do this rewiring, you have three options. It's not like two incoming arrows and two outgoing arrows. They are undirected, and you can choose to reorient them depending on how you rewire them. On the other hand, each undirected loops has two possible directed loops embedded in it. And so this rewiring property will be true if, instead of letting it rain during time 1, which is somehow the one that I used to have this rewiring property here, you let it rain twice longer. So you have twice many loops, and each loop is tossing a coin to decide in which direction to go. Then the rewiring property will be true for these oriented loops. In that case, you only have two choices when two loops meet. But then we are somehow jumping out of the bosonic, these loops carry an additional information, right? So physically, these other loops, they are just here. And the other ones, if they have an orientation, then you want to look at things like, the index around some line, the winding number, that sort of things you want to be able to measure on top of just whether the loop is there. And yeah, so I'm not going to, but it's exactly this thing where, in physics, you have these particles, the analogy, I'm not saying I'm explaining anything in physics, the analogy is some particles carry some information about, some directional information, or maybe on the loop, they have some, something else, like, some element in a compact Lie group. That's the type of thing that physicists like to do, that, is moving around on this loop. And you are just looking at how these different flags at different places, interact at distance in this collection of loops. Of course, if you are looking at in the physical world, in some sense, this bosonic thing, these non-interacting loops, is degree 0. They are not interacting, so it's not interesting for them. You want something where these particle, this collection of loops might interact in this or that way. On the other hand, there are a number of things, this result I just told you. If you do any, if you sample your collection of loops, your union of loops, and you bias it by anything that does depend only on the union of loops, like you bias it by putting a higher probability for those that have more double points, for instance. Right? So you like it when these loops pile up. Then this switching property and this rewiring property, everything I said is still true. Because the bijection will remain, will not change this weighting. So all these things will still be true for classes of actual interacting particles. So this thing where you weight by the number of double points, this was a model that was very popular in physics at some point, the 5-4 model, and there are still a number of works on this in 3 dimensions these days, which is exactly of that sort. So it's not just about non-interacting loops. You have these features are probably working for some of them. And again, having orientation, you say, okay, well, there's not just gravity around, right? So you have electric currents, magnetic stuff, something which has plus and minuses in it, and you might want to try to play with that. But that's just, again, disclaimer, especially then, this is broadcasted, I have to be very careful. I'm not doing any physics. This is just like what a mathematician is doing and dreaming about, not claiming to solve anything. It's just, playing around with fun math structures. If you're stuck on a desert island and you have the bad idea of not talking to anyone for a while, and that's, what you come out with. Okay. So I guess, there's maybe one last question over there, and then yeah.
Hi. So yeah, really, really awesome talk. I was actually, and this might be a bad question, So we know that there's like a different probability for different kind of loops and like in getting to different points in these loops. So can we use that to like infer ideas about the structure of the graph that we're working in, or do some things like that?
Yeah. Okay. So I see two questions. So the first one is, of course, it's a standard thing. You are given a graph you don't know much about, and you ask the question, can you say anything about it? Yeah. And the answer is yes. And for people from geometric analysis, and I mean, Anna here will recognize something in what I'm saying, is like, as I said, the only piece of information we use in order to build all this has to do with the Laplacian. The Laplacian is, it has to do with isotropy, which has to do with the Laplacian and the notion of harmonic functions. There is this thing around called the determinant of the Laplacian, and the determinant of Laplacian is like a determinant of a matrix, has to be, sum of. So if you know how to compute determinants of n time n matrices, you take sums over, cycles in the picture, and in some sense, this decomposition into loops has to do very clearly, directly related to things that people have been, playing with in order to probe, there's this general thing that, if you want to understand, groups and classify, classify groups or something, then you can say, well, how does random walk behave on that group? And then information about that might be able to tell you that two groups are different because the random walks on these two groups behave differently. So that's another example, right? And in some sense, there are works, using this collection of loops in order to, go back to very basic, questions from complex analysis, classifying, the invariance by, the properties of these collection of loops. Now, the clusters of loops and so on, I'm not so sure about the geometry that is around there. One little thing I should emphasize is that this sort of hints to the fact, this whole story is that there is a very important, canonical object around us, which is these clusters of loops, right? And in the case, if you do that in 2 dimensions, these clusters of loops, their boundaries, and these are exactly these stochastic Löwe evolutions type object. They have a fractal dimension 3/2. The boundaries of the loops and the fractal dimension of the cluster of loops will be 15/8. So you could do lots of things in 2 dimensions. And in 3 dimensions, and now I'm cheating a little bit, but it's sort of pretty clear that these clusters of loops, Brownian motions, I should have said that at some point earlier, but now I remember, Brownian motion has these fractal curves. They are a bit fat, they are 2-dimensionals. So therefore, if you take 2-dimensional and 3-dimensional space, they actually can intersect. So indeed, there will be chain of loops in 3 dimensions, of these Brownian loops in 3 dimensions. If they would be circles, they would miss each other, but they are a bit thicker. And because of the scale invariance, you would expect that the cluster will be higher fractal dimension than the loops themselves. And it will be 2.5, exactly, 5/2. So somehow these connections, are created by these fractal structures in 3-dimensional space, which have dimension 2.5. Yeah. And you could move, this works in any dimension. There are different stories in higher dimensions. So if you are in dimension 5, that's sort of probably the super interesting one, because there's an overlay of macroscopic and microscopic stuff, which you can also play with, but that's for another talk.
Well, thank you very much, Wendelin. It's been a great talk. Thank you very much.